All right, so last time we were in the middle of section 5.4, we had gone through a little bit about logs, how to change between exponential and log form. We went over the 4 basic properties that we use with logs. And the last thing we're going to look at is how to take logs that are separate and combine them. Or if they're already combined, you can separate them. You can do it either way. And there's 3 properties that we use here. So the first property has to do with if you have a product inside the parentheses, okay, like m times n. You can separate that into 2 logs. Whenever you have a product, it separates as a sum. Notice the base on the log stays the same the whole time. So whatever the base was to start, that's going to be the base when you split it. The first argument when you split it is your first factor. Your second argument is your second factor. So here's an example with all numbers. And I'll type that in so you can see it. So it says log base a of 4 times 5 would equal log base a 4 plus log base a of 5. Now, when I do it on the calculator, there's 2 bases that the calculator can do quickly. It has buttons built in for them. Does anybody remember what the 2 bases are that are built into the calculator, Shai?
E and 10.
Yes, E and 10. I'm telling you that this formula works for any base. It's just easiest for me to show you with base 10, because I got a button for it. Okay, so that's how I'll show you. So let's take the log of 4 times 5, which is just 20. Okay, you get that. And now let's take log 4 plus log 5. Get exactly the same thing. What are 2 other numbers you could multiply to get 20 besides 4 and 5? Yeah, so I could do 2 and 10. Log 2 plus log 10. Any 2 numbers that multiply to give me 20 will work. You could do 40 and a half. That's fine too. Any questions on that idea? So a product splits as a sum. Next one we're going to look at is a division, okay, a fraction. How do you think a fraction would split? If it's similar to the last formula, but not exactly the same. Jake? It's going to be subtraction. Okay, got to be a little bit more careful here because subtraction, you got to put it in the right order. Addition, not really that important. Okay, when you add 2 numbers, the order doesn't matter. But with a fraction, it's the log of the top minus the log of the bottom in that order. Okay, so here's another example with numbers. I'm not going to type that one in, but it works. It works with numbers. Okay, and it also, again, it even works with base E. So you could write out the same thing with LNs. It works with logs of any base. Okay, so that's our second rule. And our third rule. The third rule allows you to take exponents if they're on the argument to a log and put them in front. Okay, you can't just take exponents and put them in front in general, but you can if you have a log. All right. So here's an example with numbers. I'll type that one in so you can see it. So it says the log of 3 to the 5th is the same as 5 log 3. All right, so the log of 3 to the 5th, oops, log 3 to the 5th. And now if I type in 5 log 3, I get the same thing. That one's important because what it does is it gets rid of exponents. That's really handy if you have variables that are in the exponent. Okay, we don't like to have variables up in the exponent. Now we have a way to get them out of the exponent. It doesn't get rid of it, but at least it's not in the exponent anymore. That makes it easier. Now, there's going to be one case where you have an exponent it's almost hidden. And we talked about this, and usually it's easier to remember because we do it in the same week, but we did this last week. When we talked about radical functions, raising something to a 1/2 power is the same as taking the square root. Okay. The reason that's going to be important is because if you had something like this, and I said to you to rewrite this problem without exponents, and you look at it and you say there is no exponent, I'd say there is. It's hidden in the square root. So that really means this. Right? Square root is the same as to a 1/2 power, and now you can put the 1/2 in front. So that's an example of writing something without any exponents. This has an exponent that's visible. This has an exponent that's hidden. Okay, think of it that way. It's hidden in the square root. That's the only one that would ever be hidden that you got to remember. Okay, any questions on that? Okay, so we'll try a few examples, combining logs and then splitting them, and that'll finish up this section. All right, so the directions say to take what you have here and separate it into multiple logs, and it says to express powers as factors. This means to do Rule 3. Don't leave things as powers. Put them in front as multiplication, as a factor. Okay, so let's split this up. All right, I see a product inside the parentheses. So Isabel, when I have a product, does that split as a sum or a difference?
Sum.
It's going to be a sum. So we're going to have a sum of 2 logs. Isaac, what's going to be the base on each log?
4.
4 stays exactly the same as the original. And Nick, my argument to my first log?
3.
3. Losing my voice. And my argument to my second log?
4. X.
X. There you go. And there's your answer. So log base 4, 3 plus log base 4, X. That's it. That's the whole thing. Any questions on that? I mean, you get a little bit harder, but that's pretty much the general idea. You're separating it out. Let's try this one. So log base 2 of 5 times r cubed. So Jaden, is this one going to split as a sum or difference? Okay, how come?
Because of the exponent. Or because of the R, actually.
So the letter and the exponent don't tell us necessarily whether it's going to be a sum or difference. What tells us if it's a sum or difference? We're looking for either this in parentheses or something else. Yep.
Product or quotient.
If it's a product or a quotient. This one is still a product. Okay. There's no fraction here, so it's still going to be a sum. It's something times something. The second something is a little more complicated, but it's still something times something. So we're going to have log. Connor, my base on each log?
2.
2. 2. 2. Rebecca, my first argument?
5.
5. And Kylie, my second argument?
R.
It would be r cubed. But now the directions said to write powers as factors. So what are we going to do with the 3? Emily? We're going to put it in front. So it would have been r cubed. Then you're going to put the 3 in front. And you're done. Okay. Any questions on that one? All right, let's try this one. Log base 9 of x divided by 2. Okay, so Greta, is this one going to split sum or difference?
Difference.
Yeah, this time you got a fraction, so we know we're going to subtract 2 logs. So So log minus log. And Harris, what's going to be the base on each log?
I'm not sure.
All right. What was the base on the original?
I'm still not sure. I wasn't here Friday.
Oh, okay. So the base is the number that's lower than everything else in the problem.
2.
That's outside the argument.
9.
9. So the base is the number that's right next to the log, but it's just written a little bit lower. So base 9. Base 9. Base 9. And Emily, my first argument, x, and Sam, my second argument, 2. And that's it. Let's try this one. So even though this is an ln, we can do it the same way. Your final answer will just have ln's. Don't change them to log base e. Use the abbreviation. Anyone think they could tell me the whole answer, final answer, if you do this one out? Sam?
3, the log base e of y minus the log base e of e.
Yep, and we'll just leave it as ln because that's the abbreviation, so you can pronounce it as ln, that's fine, but what you said was correct. Yep, and that's it. Any question on that one? Okay, so we've taken a bunch of problems and separated them. Now, let's take and recombine them. So this is exactly what we just did, except in reverse. So now it says express factors as powers. That means do not leave numbers in front. You should put them back up as exponents. So it's the reverse of what we just did. So Megan, is there any number there that we should put back as an exponent?
4.
The 4, yep. So we're going to have log base a 7 plus log base a of 3 to the 4th. Now, if you end up with an expression that you can do out, you should. Okay, so we can do 3 to the 4th. I think we just did that in the homework. Does anyone remember what 3 to the 4th power came out to? 81. Now at this point, once you've combined it to 81, you would have really no way to go back. Like if I covered everything above it, you wouldn't know how I got 81. Like, was it, 9 times 9 or 3 to the 4th? You wouldn't know. So once you combine it, this is kind of like a one-way process. You can't really go back. Okay, so now we have two logs that are a sum. We're going to have a single log. And the 7 and the 81 are going to get combined in one of two ways, multiplying or dividing. Yep, they're multiplied. So we have 7 times 81. Again, that's something we should do out. So it's log base A of 567. So I kind of like doing this way better because at each step it gets smaller. Versus the way we did it before, it gets more complicated at each step. Any question on that one? All right, this one, I think I need to fix one of the numbers. Let's make this, because 3 to the 4th is 81. I don't want to get 0 here. Let's make this 80. That works. All right, so 2/3 ln 8 minus the ln of 3 to the 4th minus 80. Okay, Madison, what's the first thing I should do here?
With the 2/3 of the power.
Yep, we're going to put the 2/3 back as an exponent. So it's going to be ln of 8 to the 2/3 minus the ln, and let's do that out. So 3 to the 4th is 81, and then 81 minus 80 is just 1. And again, that's another homework problem. The log of 1, doesn't matter what the base is. What's the ln of 1? 0. So we don't even need the last part this time. I'll leave it for now, but we really don't need it. Okay, 8 to the 2/3. Okay, kind of off to the side, the way you can do that is what you divide by is a root. The numerator is a power. So it's 8 squared. So we're going to think of it that way. 8 squared, and then take the cube root. So what's 8 to the second power? 64, yep. So it's like we just did that part. And now divided by 3 and an exponent means take a cube root. Just like divided by 2 means take a square root. So I've got 64, and then the cube root of 64 is how much? 4. So I get ln of 4 minus the ln of 1. Now, let's pretend you didn't know the ln of 1 was 0. Okay, at this point, I'm really done. How would these be recombined? If you had subtraction, the 4 and the 1 would be recombined using what? Division, yep. So this is why the 1 doesn't really matter, because 4 divided by 1 is still just 4. Okay. So it's just the ln of 4. Or if you recognize the ln of 1 is 0, you could have just crossed it out right there as well. Okay, any questions on that? Okay. So the homework from this part, you've already done all of those. Okay, so it's just those 4 questions, 29, 30, 31, 32. Okay, so last thing we're going to look at is 5.4 part 2. Okay, well, that'll finish up 5.4 for us today. And it's on a little bit more with log functions, and then I think we're also going to graph something on the calculator. All right, so homework a couple nights ago, we did problems like, bacteria doubling or population of a town increasing, things like that, and we solved it on the calculator. So we would graph 2 curves, something like that, and then the answer would be, how would we find it? An intercept. Okay? We would calculate where they cross. Well, now we're going to look at solving an equation, but this time we're going to do it algebraically. Okay, so we're just going to try to do it without a graphing calculator. So I told you that last week I said next week we're going to do a problem. It's exactly the same problem, same numbers. We're just going to do it a different way. Okay, this is the same problem from last week. So it's a town with a population of 50,000 people, increasing at a rate of 2.5% every year. How long will it take the population to hit 100,000? So let's take a look. First thing I need is I just got to write out an equation. Okay, so anytime I do exponential growth, what's always the very first thing in the formula? Yep.
Like your initial amount.
An initial amount. Yep. So initial amount times, and does anyone remember what goes in the parentheses? It's something plus something. Yep.
1 plus
the rate.
1 plus the rate raised to the number of years or the time that's gone by. Okay, so let's fill this in. So my initial population is how much? 50,000. Times 1 plus my rate. Now my rate is 2.5%. What's 2.5% as a decimal? 0.025 plus 1. 1.025. And so this is my population, and they want to know when the population reaches how much? 100,000. So I'm going to plug in 100,000 for the amount. Okay, so my goal is to get t by itself. I can't do that directly yet, but there is something I can move away from the right-hand side over to the left. Does anyone see the 50,000? How would you move it? If there was an addition sign right there, then you would subtract, which I can't get rid of now. Yep, we're going to divide. So divide by 50,000. Divide by 50,000. What do I get on the left? What's 100,000 divided by 50,000?
2.
2. Great. So 2 equals 1.025 to the t. Now, that's not a problem you'd see in Algebra 1. Why? What makes this problem a little more difficult than like an Algebra 1 equation? What about it? It's not that there's a lot of stuff in it. I mean, it's pretty short. Just 2 numbers and 11. The t is the exponent. We don't want to have the variable in the exponent. So I can take exponents and bring them in front as long as I have what kind of equation? What kind? A log. So you can bring that t and put it in front as long as you take the log of both sides. That's the only time you're allowed to do it. So just like you can take the square root of both sides, you can take the log of both sides. So log 2 equals log 1.025 to the t. Now you can put the t in front. Log 2 equals t times log 1.025. Now what I have here is basically like this. Number equals letter times another number. I want to get the letter by itself. So how would I get t by itself?
Subtract the log of 1.025.
So would you subtract 5 from both sides here?
Oh, yeah. No, I was looking at the top and the divide. My apologies.
Divide, yep. Because remember, it's multiplication. So if you want to get rid of a number that's multiplied, you have to divide. So divide. And don't worry about what the log is. Just divide by whatever it is. Log 1.025. Log 1.025. And there is your answer for t. So we'll do it out in a second, but in terms of algebra, it's really not that much. It's a couple steps, and the trickiest thing is just taking the log of both sides, and that allows you to bring the exponent in front. Without that, we would have been stuck. Okay, we wouldn't have really known what to do with that letter up in the exponent. All right, so we've got log 2 divided by log 1.025. So it's going to take about 28.07 years. And if you look back at the notes whenever we did this, we got exactly the same answer doing it graphing. So if I had to do a lot of these problems, I would almost try to come up with a shortcut based off looking at the final answer. I'd say, well, it looks like the denominator is just the log of 1 plus r. That's all that the denominator is. And the numerator is the log of, let's see, that was our final population divided by initial population. Final was 100,000. Initial was 50,000. So if you think of it that way, you wouldn't even have to go through any of these steps. Just do log of final divided by initial divided by the log of 1 plus r. And there's a shortcut for doing the problem every time. Or if you don't remember it, do what we just did every time. Okay. Any questions on that? All right. Okay, so last thing. So in Algebra 1, sometimes you have like a set of data points, okay, and you try to find like a line that goes through them. Okay. So let's say you had a set of data points like that. They're not perfectly in a line. But if I draw that in, that looks pretty good. And I've modeled the data with what's called a line of fit. Now in statistics, there's a way to calculate the best possible line like ever. Like you can find the best slope and the best intercept, and there's no guessing at all. Like I just guessed. And the way you do it has to do with what's called residuals, and you look at the distance of points from lines, and you do all kinds of things, but it's more of a statistics thing. And lines are good if your data looks straight, but data like this, it wouldn't be good to use a line. Okay. Line might be good for the bottom part. I'd say it's pretty accurate in that section. But if you use that line to continue what's going to predict later on, it's way off. Okay? What we should use here is a curve. So something more like this. That's a better predictor of our data. So what I'm going to do is show you how the calculator can find that curve for us automatically if you're given a set of data. Okay. And these particular points are the kind of curve we're going to look at. It's called a power model or a power function. Remember, there's all kinds of curves. Maybe a parabola, that's a curve. Power function, that's another kind of curve. And that's what I'm going to show you how to do. All right, so I'm going to write down some of the steps as I go. You might have to go back and look at the video if you get tripped up with like, well, what button did he press? You know, you'll be able to see it again. But it's all going to be on the calculator. And your final answer is going to look something like what's in that box. The calculator will tell you the A, and it'll tell you the M. So if A was 2 and M was 3, your final answer would look like this, 2x cubed. Okay, but the calculator will tell you A and M. Now, the calculator might use different letters. It doesn't matter what the calculator calls them. It'll tell you the number in front, and it'll tell you the exponent. Okay, whatever it wants to call them. All right, so let me give you, let's look at a set of data. All right, so for this one, I don't want to determine if a power model is appropriate. I just want to find a power model for the data. So just change the directions to that. Find a power model for this data. Part of what you should do is check and see, is this even the right type of data to use a power model for? Right? A power model is a tool. You don't use it all the time. You should know what to use it on and what not to use it on. I'm already telling you this is a good set of data for a power model. You're not going to have to check whether or not you should use it. Okay. All right, so to find a power model for this data, what do you think the first thing I have to do with all these x and y values is? I have to plug them all in. I have to tell the calculator what they are. So on the calculator, after you turn it on, you're going to go to Stat, and then you're going to go to Edit. Now, I've done this problem a couple times, so it might already have some numbers in here from a previous class if you're using one of mine. So just make sure you know how to type them in yourself. Just if you have numbers in there you don't want, just highlight the number and press delete. Don't highlight the L1 and press delete, because then what it'll do is it'll delete this whole column. The only way I know how to get it back is just to reset the whole calculator. There's a way to get it back without doing that, but it's the only way that I know. So one of these columns is going to be the x's, the other one will be the y's. Technically, you can pick whichever one you want to be whichever one you want. But I would put the x's in L1 and the y's in L2, and it'll save you a couple steps later on. Yeah.
How did you get there?
You go to Stat and you go to Edit.
Stat.
Yep. So you press Stat's right below Delete, and then you go to Edit. Okay. So for the x's, I'm going to put in 1, 3, 5, 8. You hit Enter between each one. Now, to put in the y's, just press the right arrow. It'll bring you over to L2. And now type in those numbers. So 5, 31.2, 73.1, and 160. Okay, so now we've put all the data in. You don't need to save it. It's automatically saved. You can just press second, quit, and it's all in there. If you want to see it again, just go to Stat, Edit, and it's still there. Okay. Any questions on just typing it in? Okay. So now we're going to go back to Stat, except this time we're going to go to Calculate. So we go over to Calculate, and we have to pick what we want the calculator to calculate. We want it to find a power function. Okay. I don't think it calls it exactly a power function. I think the calculator calls it a power model. So if you press down, or actually it's probably faster to go up because it's at the very bottom of the list. Power regression. Okay, so on my calculator it's option A, but if you're using a different one, it's the one that says, bless you.
Thank you.
Power regression. Okay. Once you're on power regression, just hit Enter. Now, notice it's asking me a question. It's saying, where should I get the x's from? Where should I get the y's from? I told you to just put the x's in L1 and the y's in L2. That's so you don't have to change anything right here. If you decided to use, say, list 3 and list 4, you'd have to change that right now. As long as you did what I said, you should be fine. If you're wondering how do you type L1 in, you press second, and then 1, 2, 3, 4, 5, 6. Those are all your lists. Second, and then 1 through 6. All right, I don't need to change anything. So I can go right down and calculate. Hit Enter. And it tells me, here's the formula. Y equals ax to the b. So it uses a little bit different letter. A is basically what number? 5. All right, when it's 0.999 4 times, it's pretty close to 5. And b is like 1.6 repeating. So it's like 1 2/3. Right? So let's write that out. What's 1 2/3 as an improper fraction? 5/3. All right. So b is about 5/3. A is about 5. So fill that in. Y equals 5 x to the 5/3. And that's the equation of the curve that would go right through these points as accurately as possible. Okay. Now, I'm going to see how accurately by graphing. But any questions on that equation first? Okay, so what you have here in this table, that's a scatter plot of data. So what I'm going to do is press second, y equals. I can do up to 3 scatter plots at the same time. Okay. I'm going to do one set of data with x's and y's. So once you press second stat plot, hit enter on plot 1. Okay. What I want to do is I want to turn it on. So it's actually going to put these as dots on the screen. Now I can change it. I can make it like a line graph or a bar graph or a box and whisker plot. Don't worry about the type. The first type is fine. The x's are in L1, the y's are in L2. I can also change what kind of dot it puts on the screen. Little boxes or plus signs. That doesn't matter. And I can change the color of the dots. Again, blue is fine. Okay, so now we've turned the scatter plot on. And notice plot 1 is highlighted. If you press y equals again, plot 1 is still highlighted, which means it's on. Now, let's just move this over a little bit. What's my highest x value in that list? 8. So I'm going to go to 10 on my x max. That's fine. What's my lowest x value? 1. So I'm going to set my x min at 0. All right. What's my highest y value? 160, and my lowest is 5. So I would say for a low, you could go 0. For a high, 180 is probably fine. And I haven't typed in this equation yet. All I'm doing is graphing the dots. So if I hit graph, there's 4 boxes, each box representing one of the coordinates. If I trace 1, 5, 331.2, 573.1, 8, 160. It's just the 4 dots. Now, I want to type this in and see how closely it goes through those points. So if you go to y equals, type in that equation. 5x to the 5/3. 5/3. Okay, it's still going to leave the dots in the background. It's just going to put a curve right in front of them. And you can see that that curve is pretty good. In fact, it's pretty much perfect. Goes right through the points. So now if you wanted to predict, like, well, what about if x was 4? What would the y value be? Well, now you can use that curve to predict it. If x is 4, based on that curve, y would be about 50, a little over 50. And that's it. That's how you find a power model. Any questions on how we did that? Okay, again, it's the kind of thing like on your reference sheet, you might want to go back at the video and just look at like, okay, you press this, you press that, and then you might want to break it down that way. It's up to you. All right. So 5.5, we're going to do that part tomorrow, which is not super long. So the homework tonight is the 29 to 32 on the page I already showed you. Plus on 293, I might take one of those off. Just give me 1 second. 35, 36, 33. Yeah, you don't have to worry about 35. So on that page, just 36, 43, 46, 48. Don't worry about 301. If you want to write it, that's tomorrow's. If you want to copy it. 301 is not due tomorrow. So you got 4 problems from the other page, and then 4 problems for tonight, so you got about 8 problems to do. Okay. Also, I will be after school today, because Tuesday I have a meeting, and Wednesday is a half day. So if you need to come, I'll be here today for a little bit.